Hello, I'm Mr. Bob, and welcome to my Algebra 1 video series. This video covers Chapter 3, Section 1, titled Inequalities and Their Graphs. By the end of this video, you will have reviewed methods for identifying solutions of inequalities. These skills include identifying inequalities by mental math and identifying inequalities by evaluation. From there, you will be looking at graphing and writing inequalities in one variable and writing an inequality from a graph. Finally, you will review skills for writing real-world inequalities. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find this video to be helpful. Thank you very much. Okay, before we get started into the depth of this review, let's look at a definition. Solutions of an inequality or solutions of inequalities. A solution of an inequality is a number, any number, that makes the inequality true. The solutions of an inequality x is less than 3 are all numbers that are less than 3. So negative 4 is less than 3, 2 is less than 3, negative 1,000 is less than 3. These all make this inequality true. 7 is greater than 3. So this 7 does not make this inequality true. All numbers in this particular case less than 3. We could say less than or equal. That's another, you'll see that coming up. We have less than or equal, greater than or equal, less than, and greater than. When it says equal, the number could be 3. In this particular case, x is less than 3. So you can't be 3. 3 is not a solution to this inequality. 2 is, but 3 is not. Okay. Okay, objective 1, identifying solutions of an inequality. So just like we talked about in the definition there, a solution of an inequality is any number that makes the inequality true. The solutions of the inequality x, right here, x is greater than 10, are all numbers that are greater than 10. So if you said 11 is greater than 10, is that true? Yes, 11 is greater than 10. How about if I said 9 is greater than 10? Is that true? No, that's not true. What if I said 10 is greater than 10? Is that true? No, because 10 is equal to true. Okay, is equal to 10. So 11 is greater than 10. That's true. 9 is greater than 10. That's false. How about 10 is greater than 10? That's false. If this, when we have 4 symbols, so basically what we have equal to, so we have 5, 6 symbols, right? So we have equal to, oops, excuse me. We have equal to, we have not equal to, right? Okay. We have greater than, we have greater than or equal to, we have less than, and we have less than or equal to. Now, this symbol right here, for the 10 greater than 10, that's said it's false. What if this was great? What if it was 10 is greater than or equal to 10? Then this would have been true. So these are the symbols we use. Not equal, equal, greater than or equal, less than or equal. Okay. You'll see them as you work in algebra and as we move forward here. Okay. Okay, example 1, identifying solutions by mental math. So we're just going to look at these and think about them, right? There's not a lot of, there's no adding and subtracting going on. We're just going to look at it and make a decision. These are just like we just previously did in the previous slide. So it says, is each number a solution of x is less than or equal? Here's that less than or equal. Now you see the equal right there. The less than or equals to 7. Is x less than or equal to 7? How about for problem A? Is 9 less than or equal to 7? No, it's not, because 9 is not less than or equal to. It is not true. 9 less than or equal to 7 is not true. 9 is greater than 7. How about negative 1? Is for B, is negative 1 less than negative 7? The answer is yes. Negative 1 is definitely less than any number, 6, 5, 4, 2.5, 3.25, negative 100. They're all less than or equal to 7. And that is a true statement. This inequality is true. With negative 1 is definitely less than 7. And how about is 14 halves or are 14 halves less than or equal to 7? Yes, the answer is true. Yes, because 14 halves is equal to 7. And therefore, 14 halves is less than or equal to 7. It works with the equal piece right here, the equal to 7. And this is a true statement. Okay, example 1, check your understanding. If you're new to my videos, then I'll tell you what we usually do in check your understanding is that I pause the video and let you go ahead and take time to work these problems your own. And when you come back, then we continue on, okay? So I wait for a few seconds before I continue. Um, and if you've been with me before, you know what to do. So I'm going to read it. Is each number a solution of A is greater than or equal to minus 4.1? Okay, I'll pause the video, or I'll wait for you to pause. Okay, let's assume that you've gone through these 4. So is negative 5, for problem A, is negative 5 greater than or equal to negative 4? Or negative 4.1? The answer has to be no. It is not greater, right? No. Negative 5 is less than negative 4. Negative 5. 5 is more negative, so it is less than negative 4. How about B? Is negative 4.1 less than or equal to 4.1? Negative 4.1. Yes. The answer is yes, because negative 4.1 is equal. Here's that equal piece right there, is equal to negative 4.1. That's true. How about 8? Is 8 greater than or equal to negative 4.1? The answer is yes, because 8, anything greater, negative 3 is, 0 is, and here's D. Is 0 greater than or equal to negative 1? The answer is yes for D also, because 0 is greater than any negative number, and any positive is greater than any negative number, right? So it's pretty straightforward. Okay, example 2, identifying solutions by evaluating them. So now what we're going to do is, like in problem A, we have 3 is what we're evaluating for. So what we're going to do is we're going to end up substituting 3 for the x value. So we start by writing the inequality right here. 2 minus 5x is greater than 13. So what are we going to do? Let's substitute, take the 3 right here, the 3, and substitute it in for the x. And when we do that, we get 2 minus 5 times 3 is greater than 13. So now the question is this true or false? Well, we're going to simplify the 5 times 3 and make that 15. So we have 2 minus 15. Is that greater than 13? Well, no, because negative 13 is not. It is not greater than 13. So this is false. 3 does not make the original inequality true. So the 3 is not a solution to this inequality. Okay, how about negative 4? Is negative 4 a solution to the same inequality? So we write the inequality, 2 minus 5x is greater than 13, and we substitute the negative 4 in for x, so we get 2 minus 5 times the quantity negative 4 right here is greater than 13. We simplify 2 plus 20 minus 5 times minus 4, or negative 5 times negative 4 is 20, positive 20. 2 plus 20 is, when we simplify, 22. And is 22 greater than 13? Yes, it is true. -4 makes the inequality true. So -4 is a solution. Okay, example 2, check your understanding. I'll read the question, or what we want here is each number a solution for 6x minus 3 greater than 10? So we have problems A, B, C, and D. This is check your understanding. So I'll wait. You can stop, pause the video, and give it a shot, and I'll wait for you. Okay, I'm assuming now that you've taken the time to do this work. So let's look at it. Is 1 from problem A, is 1 a solution to 6x minus 3 is that greater than 10? So I'm going to write down the equation. The equation is 6x minus 3 is that greater than 10? So what do? We substitute the x 1 for the x, and then we get 6 times 1 minus 3. Is that greater than 10? Let's simplify this. We're going to get 6 times 1 is 6, minus 3 is 3, greater than 10. Is 3 greater than 10? The answer is no. So 1 is not a solution, not a solution. It is not. How about 2? Is 2 a solution? 6x minus 3 greater than 10? Substitute 2 for the x. 6 times 2 minus 3, is that greater than 10? Now we do the multiplication here and simplify. We're going to get 12 minus 3 is 9. Is 9 greater than 10? No, it is not. 2, not a solution. Okay, how about 3? You see what's happening as we're moving 1, 2, 3, and 4. We're getting closer, I think. So let's try 3. 6x minus 3 is greater than 10. Yes or no? Substitute 6 times 3 minus 3. Is that greater than 10? We'll do the multiplication and simplify. So we're going to get 18 minus 3 is 15. And is 15 greater than 10? Well, the answer is yes. It is. 3 is, excuse me, let me erase that, is a solution. And how about 4? Well, 1 was not, 2 was not, 3 is, we're going to guess 4 is, right? 6x minus 3, is that greater than 10? 6 times 4 minus 3 greater than 10? That's our question. Put a little question mark up there. How's that? Huh? Little question mark? 24 minus 3 is 21. Is that greater than 10? Yes. Oops. Yes. 4 is a solution. Okay. Good job. Okay, objective 2. Graphing and writing inequalities in one variable. Since the solution of an inequality is not just one number, you can use a graph to indicate all the solutions to that inequality. But before we get into the graphing, I want to remind you of something you've probably learned in the past, which is that if you do have a line, let's say we have a graph here, okay, and here are some numbers on the line, on our number line. We start at 0 here, 1, 2, 3. Here's -1 and -2, okay? If I want to talk about including or not including the number when I'm drawing a line, I can draw the line from, say, 1, and I can draw that line here to the left, okay, or to the right, rather, excuse me. I can draw this arrow, and when I put an arrow on this number line, like I just did, or if I make it red, it'll even be more obvious. If I put it like this and I go red all along here, that means every one of the numbers that are underneath that line, which are infinite, forever, this arrow points to forever, infinity, positive infinity, are included in part of this line, right? But do we include, I started at 1, do we include the 1 or not when we're drawing? See, we know that automatically 2 is included, 3 is included, but is 1 included? Well, if there's a solid dot on the 1 is included. If, let's pretend like this started at -1 this now, if the -1 in our case here, it says we're going to, instead of 1, greater than 1, it's greater than -1, it's greater than, this is greater than or equal to 1 right here. Greater than or equal to 1. If I put a circle around here and draw the line like this, right? This says everything under the line except what I'm circling, and I'm circling the -1. So in this particular case, -1 is not included. So it'd be -1 is less than, how about that, right? All the rest of the numbers, x. -1 is less than, not included. How about for this one here, it would be +1 is less than or equal to x. Okay, so if it's a solid dot, it's included. And if it's an open dot, as we call open circle, it's not including the number that it's encircling. So let's look at this below here. It says, let's look at the inequality. X is less than 3. Well, here's our graph. Here's 3. And x is all of the numbers this way, right? But the question is x included or not? No, it is not less, x is not less than or equal to 3, it's less than 3. So as we said before, you got the circle around it, right? The open dot shows that 3, right here, 3 is not in the solution. But you do shade everything to the left of that circle. That's what we did right here. We saw, how about m is greater than or equal to -2? So in this case, the dot right here on -2 says that it is included. So that m is greater than or equal to -2. So that means you include -2 and everything to the left of everything greater than -2 is included. The closed dot shows that -2 right here is a solution. And then you shade everything to the right, okay? And then how about this? -1 is greater than or equal to a. Well, here's -1 greater than or equal. So we're going to include the -1 in our, now just does the line go to the left or the line go to the right? Well, it says that -1 is greater than whatever a could possibly be. So that means that here's -1. So -1 has to be greater than or equal to anything and every dot available. So the closed dot again shows that -1 is one of the solutions. And there are an infinite number of solutions, because this line says going on for infinity and going down as small as you possibly can. Every possible number, every possible real number at this point in this inequality is available to us according to the rules of the inequality. Okay, example 3, graphing inequalities. So let's graph a couple here. So it's problem A. Graph C is greater than, right here, C is greater than -2. So I put a line on here for us, so we'll give us a nice straight place to start from. And I'm going to write some numbers on the line. I'm going to start here at 0. This is our 0. -1, -2, -3, -3, -2, -1, 1, 2, 3, 1, 2, 3. So now it says C, all numbers greater than -2. Well, here's -2. So since it's not equal, what do? We have to put a circle. I'm going to change colors here. Let's change it to a red. So we're going to put a circle around the -2 because we cannot include the -2. And then we're going to take it from the circle. We're going to go everything saying that C is greater than the number -2. And C is every solution to the inequality. So -2 is not a solution, but every other number to the right of it is. How about graphing 4 is less than or equal to M? Well, 4, right? So I'm going to put M0 here. Let me keep these consistent. I'm going to put 0. Oh, that's the eraser. We're going to put 0 here. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. And it says here that 4, I'll start with drawing a circle. Okay. 4 is less than or equal. Oh, so I get to fill in the circle because it says or equal, right? And 4 is less than M. So does that mean that we go this way, less than? Or is the M has to be greater than 4? Because 4 is less than or equal to M. So that means that we're going to go this way, right? All numbers making 4 less than or equal to 4. So our numbers are all these numbers, 4 and everything greater than 4. Okay. Okay. Example 3, check your understanding. So it says graph each inequality. So I wrote out the problems and I put down some lines for you to start with, make it nice and straight line for you. I'll go ahead and wait here while you pause the video and come back. And then when you come back, we'll do it. I'll wait here 5 seconds. Okay, I'm going to assume that you've worked these and you're ready to move on. So let's give them a shot. So problem A says graph each inequality. A is less than 1. So what am I going to do? I'm going to write down, I'll do 0, 1, because that's the key here. 2, -1, -2. How's that? Okay, we got a few of them. We could do the 3. It doesn't really matter. 3. So 1 is less than. There's no equal sign, so I can put a circle. I'm going to change colors to red. I can put a circle around the 1 because I'm not going to include it. Now I just have to decide, am I going to put the red out to the right or out to the left? It says A, that's the line, values of the line, are less than 1. So that means A has to be everything here to the left, less than 1. Okay? How about B over here? -3. So I'm going to start -3, -2, -1, 0. And I'll do -4, -4, and -5. Okay, so it's n is less than or equal to. Oh, I'm going to change colors again. I'll go back to the blue this time. So now we're going to do the 3, -3. Here's the open circle. Is it open or closed? Oh, see that? We got a negative sign, an equal sign right there. So that means we're going to close the dot on the -3. And now n is greater than or equal to -3. So that means that n is all the values that we're going to color in, and that's everything greater than 3. -3 rather. So here it is. The value is greater than -3. All these values over here are all greater than -3. And we can include -3 because of our greater than or equal. So we included it. Here we got the solid dot. Okay, now 2 is greater than P. So let's do this. 0, 1, 2, 3, 1, 2, 3, 4, 5, 4, 5. So 2 is the number we're dealing with. I'll put a -1 in here and a -2. Okay, so 2. Right here, I'm going to start with an open 2. And I think I'll change colors. Then we'll go back and forth. Red, blue, red, blue. I have an open 2. and I see that there's no equal sign, so it's going to stay open. And what does it say? It says my p-values, 2 is greater than my p, anything the p is. So if p is a 0, 2 is greater than 0, correct? So that 0 is included, so that means I'm going to go everything to the left. Everything on the number line forever. Unless, yeah, there's no reason to stop. Unless there was a part of the problem, a real world problem where you'd only go so far for some reason. Anyways, open circle here, open circle, open circle, closed circle. Less than, less than, greater than or equal, greater than, no equals there, right? Okay. Okay, example 4, writing an inequality from a graph. So now we're going to go backwards. We're going to take a look at the graph and then write what the inequality is. So let's take a look at these. Problem A, write the inequality for each graph. A. So, and these are all drawn out for us, right? So it says we have an open -4, so that means we don't, there's not an equal to -4. So it's going to be something less than or greater. And so the values, the colored in line part, are the values of our x. And the x's here are less than -4 and not including -4. So when we look at it, we see x is less than -4. Numbers less than 4 are graphed. That's what we've done here. These are our x values. What are our x values in this one? We have a dot, a closed dot, way out here on 5. Well, that means that we're going to include the 5, so it's going to be something about greater than or equal to 5, right? Well, we're going to say x. This is our x. All the red, everything in red is an x value. So x is what? Everything that is less than and equal to 5, because all of these are less than 5. So here's x is less than or equal to, right there, equal to, right there, less than or equal to. How about C? C says x is greater than 1/2. Well, where is 1/2? And it says greater than, doesn't say equal to 1/2. So we're going to find 1/2. Apparently it's right about here. And we're going to put a circle around it. Right there. It's greater, x is greater. So all the colored in on the graph, everything that's colored in on the graph on our line are the x values. And x is greater than 1/2. So everything to the right of the circle. But it is not a dot because there's no line. There's no line under here saying greater than or equal to. So we're not going to use that equal there, right? Can't do that. And how about the last one? We have a dot, not an open circle, a dot on -1. So we know it's x is something to do with -1. And the x values are all the colored part of the line. So, and these are all greater than the -1. They're all above -1 goes 0, 1, 2, 3. We don't get the negative any 3, -4. It's just from -1, including the -1. So that's going to be x is greater than, the colored area is greater than or equal to, here's the dot, -1. Numbers greater than or equal to -1 are graphed. Okay, example 4, check your understanding. So you see it says write an inequality like we just did in the previous slide for each graph. So why don't you go ahead, stop the video, and I'll wait. I'll give you some time to try them, and then when you come back, we'll do them together. Okay, I'm assuming you've done that, and you've looked at these, so let's do them. Problems A and B. So we have A has a graph with a dot on 2. So that means we're going to include, now whether it's greater than or less than, we haven't decided yet, but it's certainly going to have a line underneath. It's equal to the -2. So we're going to say x, right? X is x greater than 2 or less than 2? It's greater than. So we can say here that x is greater than or equal to 2. Greater than or equal. It's greater than here, and it's also equal right there. How about the next one? B. 0 is where the dot is. Yes, dot is, but it's not a dot. It's an open circle, right? So, and x, our x values, the colored ones, are all less than that 0, right? So we're going to write x is less than, do we include it? No, do not put the line underneath. Less than 0. Okay, I'm sure you all did those. Those are pretty straightforward. Do the slide again if it's at all confusing. Okay, example 5. It's a real world problem. So define a variable and write an inequality for each situation. So let's try it. The first one here, the one on the left. So we've got a highway. It says maximum speed 65. And we know that in our case here in the United States, that's miles per hour, right? 65 miles per hour. So it says define a variable for what we're going to call it in the inequality. What's the variable name? And for, in this case, the legal speed. So it says the maximum speed is 65. So what does that mean? It means that you can't go over 65. Does it mean you can go 65? I'm going to say yes. It means you can go 65 also. So it says, so we're going to let S right here, S is equal to our speed. How convenient, S for speed, right? And the sign indicates that your speed down the highway must be less than or equal, and can be equal to 65 miles per hour. So in this case, the speed is less than or equal to, so you can go 60, you can go 63, 62, 55. Of course, there on highways, there are minimum speeds too, but we're not talking about that in our problem here. So let's look at the next one. Shoes. Help wanted $6.15 per hour and up. So you can make $6.15 an hour and up. So let's do this. What are we going to do our variable? Well, in this case, we did P as the variable for your pay. I guess that'd be good, huh? Your pay. And that pay per hour in dollars. And what is our inequality? It says that you can make 615, so that would imply a dot because 615 is included. It includes 615 and up. The and means you include the 615. And up means anything higher than 615. So what do we have? P is greater than or equal to. It can be 615 or it can be greater than $6, not 16, I'm sorry, $6.15 per hour. Okay, example 5, check your understanding. Thanks for hanging in there. We're at the last slide, okay? And this happens to be yours. You get to run off and do these on your own. Stop the video. I'll read the question. In part A of example 5, that's what we just did up above, can the speed be all real numbers less than or equal to 65? And then they want you to explain. So what they want to know now is are they including every real number less than or equal to 65? So this is kind of a real world thing, you know? Think about that. And then the other part is in example 5, are all real numbers greater than or equal to $6.15? Reasonable solutions for this inequality. We've already done the inequalities and explain. I'll go ahead and stop. You go ahead and stop, excuse me. I'll wait. And then you write down what you think the answer to this is, okay? It's kind of like a critical thinking kind of a problem. Think of like all the scenarios and would this be right? Does that make sense? Can it be this? Can it be that too? Oh, that kind of stuff. Give it a shot. Okay, we're back. Let's look at part A. In this question A. In part A of example 5, can the speed all real numbers less than or equal to 65? Well, since it's a real world problem, we're going to have to say no. If this was just a theoretical problem, you could say yes, it's all numbers, every possible number. But in our case, since it's a real world situation, are we going to include less than 65 miles an hour, meaning you can go minus 100 miles an hour or minus 3,000 miles an hour? Well, that would be included in all real numbers less than or equal to 65. Is how about minus or negative a million miles an hour? Is that legal? Well, it doesn't make sense is the key here, right? So you're gonna say no, it doesn't make sense. So, no, not really. You're not gonna go minus or negative a million miles an hour, right? How about the next one? Now that you saw this example, if you didn't get it, hopefully you did. If you didn't, think of this one here now. Part B of example 5 are all real numbers greater than or equal to $6.15 reasonable solutions in the real world for the inequality. Well, think you think, yeah, I guess in theoretically, as we like to say, yes. But in all reality, is someone in this shoe store going to make $1 million an hour? A million would satisfy the inequality. It's greater than $6.15. How about $1 trillion an hour? Can you make? No. So that's what they're saying. No. Again, the answer here is no. And why? Because in reality, nobody makes $1 million an hour, right? Nobody makes $1 million an hour. Can't even do 100,000. I mean, someone might make 100,000, but they're not going to do it working at a shoe store, right? Okay, so there you have it.